In this lesson, we're going to focus on integrating using inverse trig functions or involving inverse trig functions. So first, some facts to be aware of. The integral of du over the square root of a squared minus u squared is equal to the inverse sine of u over a plus c, where a is a constant and u is some variable expression. And the integral of du over a squared plus u squared equals 1 over a times the inverse tangent of u over a plus c, where a is a constant and u is some variable expression. So let's implement these in a number of examples. First, let's integrate dx of the square root of 1 minus x squared. Well, this looks just like the inverse sine integral, so this should integrate into the inverse sine of u, which in this case would be x, over a, which in this case would be 1, plus c, or the inverse sine of x. Now something that's a bit different, what is the integral of, but related, dx over the square root of 4 minus x squared? Well, one thing to notice is that 4 is 2 squared, and this fits the form of inverse sine, so the integral would be the inverse sine of, in this case, x over 2 plus c. Now you might be wondering, what about the chain rule? Like, how does this come into play? Well, let's consider what would happen if we took the derivative of the inverse sine of x over 2 and just did it the way we've been approaching it. So if y equals the inverse sine of x over 2, then the derivative would be 1 over the square root of 1 minus x over 2 squared times 1/2. So let's simplify this a bit so we can see the relationship. This becomes 1 over the 2 times the square root of 1 minus x squared over 4. Now notice that 2 is equivalent to the square root of 4. So this is just like having the square root of 4 times the square root of 1 minus x squared over 4. And now that we can multiply both radicands together, we end up with 1 over the square root of 4 minus x squared. Right, so the chain rule relationship is taken care of with regards to the integration property that we're giving you. Let's consider another example. What is the integral of dx over 1 plus x squared? Well, this looks a lot like inverse tangent, where a is 1 and u is x, so this should be the inverse tangent of x plus c. How about a different one? What about the integral of dx over the square root of 5 minus 2x squared? Well, some things to recall. This looks a lot like inverse sine. A in this case is the square root of 5, and u in this case is the square root as x times the square root of 2. So when we integrate, we're going to end up with the inverse sine of u, which is x times the square root of 2, over a, which is the square root of 5, plus c. And if we clean this up a little bit, we're going to end up with the inverse sine of x times the square root of 10 over 5 plus c. Here we have a similar problem. What's the integral of x dx over the square root of 5 minus 2x squared? It looks like it should be related to inverse sine, but it's a little bit different. If we use U-Substitution, though, if u equals 5 minus 2x squared, then du equals negative 4x dx, or negative 1/4 du equals x dx. So if we substitute, we're going to end up with the integral of negative 1/4 u to the negative 1/2. Integrating that, we'll have u to the 1/2, and this should be times negative 1/2 plus c, and substituting back in our value of u, we get 5 minus 2x squared to the 1/2 plus c. So again, just because it looks like inverse sine doesn't mean that it is. Let's consider 4 more examples. We've got the integral of e to the x over 9 plus e to the x dx. If we let u equal 9 plus e to the x, then du equals e to the x dx. So by U-substitution, we end up with the integral of 1 over u du. And the integral of 1 over u du is the natural log of the absolute value of u plus c. And we know that u has the value of 9 plus e to the x. So we've got our final answer, the natural log of 9 plus e to the x plus c. So again, just you can't get locked into one way of thinking about things. 3 integrals left. What's the integral of x plus 2 over the square root of 4 minus x squared dx? Well, I don't want to make a silly algebra mistake. You can't take the square root of 4 minus x squared. It's not 2 minus x. That would be a terrible mistake to make. But what we can do is say, well, u must be equal to what? It's not real obvious what's going to help us. But one thing that will help us is if we break this up into 2 integrals. The first integral being x over the square root of 4 minus x squared dx. And the second integral being 2 over the square root of 4 minus x squared dx. Now if we consider these independent of one another, for this first integral I'll use U-substitution, so this will be u equals 4 minus x squared. So du equals negative 2x dx, or negative 1/2 du equals x dx. So cramming things in here, by substitution this is the integral of negative 1/2 u to the negative 1/2 du, and integrating that we'll have u to the positive 1/2 times negative 1, and that'll be plus some constant. And cleaning this up a bit, we'll have negative 4 minus x squared to the 1/2. The second part, though, looks a lot like inverse sine. In fact, if we just take the 2 out, it definitely looks like, using our property, it definitely looks like arc sine. And so this will integrate into 2 times the inverse sine of x over 2. So combining all of our pieces, we'll have negative 4 minus x squared to the 1/2 plus 2 times the inverse sine of x over 2 plus c. We've got 2 more left. We've got the integral of x plus 2 over x squared plus 4 dx, and we're going to use the same idea. What is the integral of x over x squared plus 4 dx plus the integral of 2 over x squared plus 4 dx? Dealing with the first, by U-substitution, if u equals x squared plus 4, then du equals 2x dx, or half of du equals x dx. So by substitution, we've got the integral of 1/2, or the 1/2 times the integral of 1 over u du, which becomes 1/2 the natural log of the absolute value of u plus c, or 1/2 the natural log of x squared plus 4 plus c. Dealing with the second integral, it looks a lot like an arctangent integral. I'll rewrite it this way to match it up, which means that a is 2 and u is x, so the integral of this would be 2 times 1 over a, so 1/2, times the inverse tangent of x over 2. And this will be plus c. Cleaning this up, we'll have the inverse tangent of x over 2 plus c. So altogether then, the entire integral is 1/2 the natural log of the absolute value of x squared plus 4, which has to be positive, plus the inverse tangent of x over 2 plus c. Our final problem is the integral of x cubed over x squared plus 1. We could try all sorts of different things, but one thing to consider is that this is just x cubed divided by x squared plus 1. And if we do the long division, this becomes x, and then if I multiply, I'll get x cubed plus x, and subtracting, I'll end up with negative x. So this becomes x plus negative x over x squared plus 1. And so by doing that, if I rewrite my integral into being the integral of x plus negative x over x squared plus 1 dx, or two integrals, the integral of x dx minus the integral of x over x squared plus 1 dx, we can approach this. The integral of x, well, that's just 1/2 x squared plus some constant. The integral of x over x squared plus 1, well, by U-substitution, this becomes, let's see, du is 2x dx, so 1/2 du equals x dx. So this will become 1/2 times the integral of 1 over u du, and integrating we'll get 1/2 the natural log of the absolute value of u plus c. And if we put our entire integral together, our final answer will be 1/2 x squared plus 1/2 times the natural log of x squared plus 1 plus c. So we had to use some algebra techniques to make this something that we could integrate. With the key lesson being, sometimes things will look like inverse trig and we can't get locked into that. They might be something else.